Nuclear fuel is a material that can be burned by nuclear fission or fusion to derive nuclear energy. Nuclear fuel can refer to the fuel itself, or to physical objects composed of the fuel material, mixed with structural, neutron-moderating, or neutron-reflecting materials. Most nuclear fuels contain heavy fissile elements that are capable of nuclear fission. When these fuels are struck by neutrons, they are in turn capable of emitting neutrons when they break apart. This makes possible a self-sustaining chain reaction that releases energy with a controlled rate in a nuclear reactor or with a very rapid, uncontrolled rate in a nuclear weapon. The most common fissile nuclear fuels are uranium-235 and plutonium-239. The actions of mining, refining, purifying, using, and ultimately disposing of nuclear fuel together make up the nuclear fuel cycle. Not all types of nuclear fuels create power from nuclear fission. Plutonium-238 and some other elements are used to produce small amounts of nuclear power by radioactive decay in radioisotope thermoelectric generators and other types of atomic batteries. Also, light nuclides such as tritium can be used as fuel for nuclear fusion. Nuclear fuel has the highest energy density of all practical fuel sources. Oxide fuel. For fission reactors, the fuel is usually based on the metal oxide. The oxides are used rather than the metals themselves because the oxide melting point is much higher than that of the metal and because it cannot burn, being already in the oxidized state. UOX uranium dioxide is a black semiconducting solid. It can be made by reacting uranyl nitrate with a base to form a solid. It is heated to form U3O8 that can then be converted by heating in an argon-hydrogen mixture to form UO2. The UO2 is then mixed with an organic binder and pressed into pellets. These pellets are then fired at a much higher temperature to sinter the solid. The aim is to form a dense solid which has few pores. The thermal conductivity of uranium dioxide is very low compared with that of zirconium metal, and it goes down as the temperature goes up. It is important to note that the corrosion of uranium dioxide in an aqueous environment is controlled by similar electrochemical processes to the galvanic corrosion of a metal surface. Mox mixed oxide, or Mox fuel, is a blend of plutonium and natural or depleted uranium which behaves similarly to the enriched uranium feed for which most nuclear reactors were designed. Mox fuel is an alternative to low-enriched uranium fuel used in the light water reactors which predominate nuclear power generation. Some concern has been expressed that used Mox cores will introduce new disposal challenges. Though Mox is itself a means to dispose of surplus plutonium by transmutation, reprocessing of commercial nuclear fuel to make Mox was done in the Sellafield Mox plant. As of 2015, Mox fuel is made in France, and to a lesser extent in Russia, India and Japan. China plans to develop fast breeder reactors and reprocessing. The Global Nuclear Energy Partnership is a U.S. plan to form an international partnership to see spent nuclear fuel reprocessed in a way that renders the plutonium in it usable for nuclear fuel but not for nuclear weapons. Reprocessing of spent commercial reactor nuclear fuel has not been permitted in the United States due to non-proliferation considerations. All of the other reprocessing nations have long had nuclear weapons from military-focused research reactor fuels except for Japan. Methyl fuel. Methyl fuels have the advantage of a much higher heat conductivity than oxide fuels but cannot survive equally high temperatures. Methyl fuels have a long history of use, stretching from the Clementine reactor in 1946 to many test and research reactors. Methyl fuels have the potential for the highest fissile atom density. Methyl fuels are normally alloyed, but some metal fuels have been made with pure uranium metal. Uranium alloys that have been used include uranium aluminum, uranium zirconium, uranium silicon, uranium molybdenum, and uranium zirconium hydride. Any of the aforementioned fuels can be made with plutonium and other actinides as part of a closed nuclear fuel cycle. Metal fuels have been used in water reactors and liquid metal fast breeder reactors, such as EBR-2. TRIGA fuel. TRIGA fuel is used in TRIGA reactors. The TRIGA reactor uses UZRH fuel, which has a prompt negative fuel temperature coefficient of reactivity, meaning that as the temperature of the core increases, the reactivity decreases, so it is highly unlikely for a meltdown to occur. Most cores that use this fuel are high leakage cores where the excess leaked neutrons can be utilized for research. TRIGA fuel was originally designed to use highly enriched uranium. However, in 1978, the U.S. Department of Energy launched its Reduced Enrichment for Research Test Reactors program, which promoted reactor conversion to low-enriched uranium fuel. A total of 35 TRIGA reactors have been installed at locations across the USA. A further 35 reactors have been installed in other countries. Actinide fuel in a fast neutron reactor. The minor actinides produced by neutron capture of uranium and plutonium can be used as fuel. Metal actinide fuel is typically an alloy of zirconium, uranium, plutonium, and minor actinides. It can be made inherently safe as thermal expansion of the metal alloy will increase neutron leakage. Molten plutonium alloyed with other metals to lower its melting point and encapsulated in tantalum, was tested in two experimental reactors, LAMPREI and LAMPRE2, at LANL in the 1960s. LAMPRE experienced 3 separate fuel failures during operation. Ceramic fuels. Ceramic fuels other than oxides have the advantage of high heat conductivities and melting points, but they are more prone to swelling than oxide fuels and are not understood as well. Uranium nitride. This is often the fuel of choice for reactor designs that NASA produces. One advantage is that UN has a better thermal conductivity than UO2. Uranium nitride has a very high melting point. This fuel has the disadvantage that unless 15N was used, that a large amount of 14C would be generated from the nitrogen by the reaction. As the nitrogen required for such a fuel would be so expensive, it is likely that the fuel would have to be reprocessed by pyroprocessing to enable the 15N to be recovered. It is likely that if the fuel was processed and dissolved in nitric acid, that the nitrogen enriched with 15N would be diluted with the common 14N. Uranium carbide. Much of what is known about uranium carbide is in the form of pin-type fuel elements for liquid metal fast reactors during their intense study during the 1960s and 1970s. However, recently there has been a revived interest in uranium carbide in the form of plate fuel and most notably, microfuel particles. The high thermal conductivity and high melting point makes uranium carbide an attractive fuel. In addition, because of the absence of oxygen in this fuel as well as the ability to complement a ceramic coating, uranium carbide could be the ideal fuel candidate for certain generation IV reactors such as the gas-cooled fast reactor. Liquid fuels. Liquid fuels are liquids containing dissolved nuclear fuel and have been shown to offer numerous operational advantages compared to traditional solid fuel approaches. Liquid fuel reactors offer significant safety advantages due to their inherently stable, self-adjusting reactor dynamics. This provides two major benefits: virtually eliminating the possibility of a runaway reactor meltdown, providing an automatic load-following capability which is well suited to electricity generation and high-temperature industrial heat applications. Another major advantage of the liquid core is its ability to be drained rapidly into a passively safe dump tank. Another huge advantage of the liquid core is its ability to release xenon gas, which normally acts as a neutron absorber and causes structural occlusions in solid fuel elements. In contrast, molten salt reactors are capable of retaining the fuel mixture for significantly extended periods. which not only increases fuel efficiency dramatically, but also incinerates the vast majority of its own waste as part of the normal operational characteristics. Molten salts. Molten salt fuels have nuclear fuel dissolved directly in the molten salt coolant. Molten salt-fueled reactors, such as the liquid fluoride thorium reactor, are different from molten salt-cooled reactors that do not dissolve nuclear fuel in the coolant. Molten salt fuels were used in the LFTR known as the molten salt reactor experiment, as well as other liquid core reactor experiments. The liquid fuel for the molten salt reactor was a mixture of lithium, beryllium, thorium and uranium fluorides. LiFBEF2THF4UF4. It had a peak operating temperature of 705 degrees Celsius in the experiment, but could have operated at much higher temperatures, since the boiling point of the molten salt was in excess of 1400 degrees Celsius. Aqueous solutions of uranyl salts. The aqueous homogeneous reactors use a solution of uranyl sulfate or other uranium salt in water. Historically, AHRs have all been small research reactors, not large power reactors. An AHR known as the medical isotope production system is being considered for production of medical isotopes, common physical forms of nuclear fuel. Uranium dioxide powder is compacted to cylindrical pellets and sintered at high temperatures to produce ceramic nuclear fuel pellets with a high density and well-defined physical properties and chemical composition. A grinding process is used to achieve a uniform cylindrical geometry with narrow tolerances. Such fuel pellets are then stacked and filled into the metallic tubes. The metal used for the tubes depends on the design of the reactor. Stainless steel was used in the past, but most reactors now use a zirconium alloy which, in addition to being highly corrosion resistant, has low neutron absorption. The tubes containing the fuel pellets are sealed. These tubes are called fuel rods. The finished fuel rods are grouped into fuel assemblies that are used to build up to the core of a power reactor. Cladding is the outer layer of the fuel rods, standing between the coolant and the nuclear fuel. It is made of a corrosion-resistant material with low absorption cross-section for thermal neutrons, usually zircaloy or steel in modern constructions, or magnesium with small amount of aluminium and other metals for the now obsolete Magnox reactors. Cladding prevents radioactive fission fragments from escaping the fuel into the coolant and contaminating it. Nuclear Regulatory Commission photo of unirradiated fuel pellets. NRC photo of fresh fuel pellets ready for assembly. NRC photo of fresh fuel being inspected. PWR fuel. Pressurized water reactor fuel consists of cylindrical rods put into bundles. A uranium oxide ceramic is formed into pellets and inserted into zircaloy tubes that are bundled together. The zircaloy tubes are about 1 cm in diameter, and the fuel cladding gap is filled with helium gas to improve the conduction of heat from the fuel to the cladding. There are about 179 to 264 fuel rods per fuel bundle and about 121 to 193 fuel bundles are loaded into a reactor core. Generally, the fuel bundles consist of fuel rods bundled 14 × 14 to 17 × 17. PWR fuel bundles are about 4 meters long. In PWR fuel bundles, control rods are inserted through the top directly into the fuel bundle. The fuel bundles usually are enriched several percent in 235U. The uranium oxide is dried before inserting into the tubes to try to eliminate moisture in the ceramic fuel that can lead to corrosion and hydrogen embrittlement. The zircaloy tubes are pressurized with helium to try to minimize pellet cladding interaction, which can lead to fuel rod failure over long periods. PWR fuel in boiling water reactors. The fuel is similar to PWR fuel except that the bundles are canned. That is, there is a thin tube surrounding each bundle. This is primarily done to prevent local density variations from affecting neutronics and thermal hydraulics of the reactor core. In modern BWR fuel bundles, there are either 91, 92, or 96 fuel rods per assembly depending on the manufacturer. A range between 368 assemblies for the smallest and 800 assemblies for the largest US BWR forms the reactor core. Each BWR fuel rod is backfilled with helium to a pressure of about 3 atmospheres. Can-do fuel bundles are about a half-meter long and 10 centimeters in diameter. They consist of sintered pellets in zirconium alloy tubes, welded to zirconium alloy end plates. Each bundle is roughly 20 kilograms, and a typical core loading is on the order of 4500-6500 bundles, depending on the design. Modern types typically have 37 identical fuel pins radially arranged about the long axis of the bundle, but in the past several different configurations and numbers of pins have been used. The CANFLEX bundle has 43 fuel elements, with 2 element sizes. It is also about 10 centimeters in diameter, 0.5 meters long, and weighs about 20 kilograms and replaces the 37-pin standard bundle. It has been designed specifically to increase fuel performance by utilizing 2 different pin diameters. Current can-do designs do not need enriched uranium to achieve criticality. However, some newer concepts call for low enrichment to help reduce the size of the reactors.